This video is going to be, for the most part, a review of material already covered since we've already talked about the raster data model, but I'm going to keep it consistent as we look at one particular phenomenon, this Mount Etna huge, massive landform, as we look at it across three different ways. So this is, we're going to, of course, use the raster data model, and this is a digital elevation model, or a DEM. Of course, here the Z values are represented as far as elevation above sea level. So we got from 0 to 3,308. And this is because it's in Italy, it's in meters. I used a particular color ramp. This is titled elevation number 10. And so it shows elevation being low with green and high being brown and white. So when we think about this particular DEM, it would say this had a massive attribute table. What would we have the cell, each cell would be shown, it would show its X and its Y, latitude and its longitude, but also its Z value being a specific elevation. So here, once again, we have those individual cells that contain X, Y, and Z data. So what I did here was I zoomed in a little bit closer, tried to go to the summit of Mount Etna. So it might start to, I don't know, might appear to be blurry. It's not. It's not the raster's fault, I should say. It's the computer. It's my fault. It's the the video processing fault. The raster, it's pretty good resolution. So in this particular, it's very high. It's about 30-meter resolution. So we're going to see in some cases smaller cell size, like 1 meter, and even sub 1 meter. That's a very, very, very high resolution. But 30 meters is very good, and it's commonly and widely used. So think of the resolution, once again, as the distance between sample points. And why that's important is if we have a bunch of points closer together, that means we're going to have less likelihood of missing the important variations in the surface. And so if the resolution was lower and the distance was greater, it would be more of a chance of, oh, we missed that one little hump or that one little nook. Even further, with more and more satellites and now drones up in the sky, cell size is only going to continue to decrease, subsequently leading to even greater accuracy, precision within raster data sets, and of course even bigger data sets, even computers handling even bigger amounts of information, and of course hopefully we can learn something from it. Here I'm going to zoom into a particular area as close as I can. So I zoomed into this particular yellow box. Try getting as close as I can inside the GIS, hoping to show, if you can see the variation. You can see actually the pixels. You can see the individual squares. At least I'm hoping you can see them on your particular computer screen. So what we do is, if I click on each one here, and so what I did is I clicked on that one, we got this pop-up. So what it does is it tells me, of course, it's Latin, it's long, but it's pixel value. And so 2,652 meters above sea level. So let's look at another one. This one up here in the white, you can see it's a higher elevation. That makes sense. But moral of the story here is we have an individual X and Y, but also in this case, the pixel value, the elevation would be the Z value. And so this is a very simple way to show the grid pattern and the raster data model, and its emphasis on using those grids, the grid cells in which they're evenly, regularly spaced. And so think of these as individual square polygons that are all horizontally in rows and vertically in columns. It's a lot of redundancy there, but anyway, so we have this massive grid, and that's how in this case, we're going to represent